Hi, Maria. Thanks for being here.
Hi, thanks for inviting me.
So, quick questions for you. First, quantum computers are really, really fast classical computers.
False.
Quantum computers solve all problems faster than classical computers.
False.
Quantum computers don't have any real-world applications yet.
False.
You need to have absolute zero temperature for quantum computers to work.
False.
We already have working quantum computers that outperform classical ones.
True. With some subtleties.
Okay. Quantum computers can break all the encryption.
Not yet.
The more qubits you have, automatically the more powerful is your quantum computer.
False.
Cool. A lot to unpack there, I think.
Yeah, good questions to discuss.
Okay, so if quantum computers are not really fast classical computers, and if they cannot solve all the problems faster than classical computers, what really are quantum computers and what problems do they solve?
Mm-hmm. Yeah, so there's these kind of two different aspects of what they do and how they do it. And both of them are kind of different to classical computers. So how they work and the reason that they're not just faster classical computers is because they're computing in a completely different way to the way that classical computers work. So quantum computers are making use of quantum information instead of classical information. So that's quantum information is information that's stored by manipulating superpositions of systems and letting them interact to create these entangled states that are kind of carefully controlled superpositions of large numbers of quantum systems. And that's in contrast to classical computing, where you're just controlling bits that are in one of two states instead of being able to be in a superposition of states. So this gives quantum computers a kind of entirely new way to process information because they can explore the full space of this quantum superposition that classical computers can't access. But that can lead to this myth that they're faster versions of classical computers, because it kind of leads people to think that, oh, instead of just computing in my classical way on my classical bits, I can compute everything in superposition on my quantum bits, my qubits, and then I basically have a classical computer but faster because I can do everything in parallel. And so that's kind of where this idea that they're faster classical computers can come from sometimes, because there's this idea of using superposition, you can do things in parallel.
Mm-hmm.
And there's some extent to which it's true that you can put stuff in superposition and then apply operations to each part of the superposition so that you're doing things in parallel. But the reason that it's not so straightforward is because to retrieve the outcome of a quantum computation, you have to measure your quantum system to get some outcome. The outcome will be presented as a classical bit, as a fixed state or sequence of states that are just 0 or 1. You can't measure and then get a superposition as your measurement outcome. You're always going to get a fixed state as your measurement outcome. So this is kind of the idea of that you collapse a quantum state when you look at it, so that when you observe Schrödinger's cat, it becomes dead or alive. That happens with qubits, that when you measure them, they become 0 or 1. And to get the outcome of a computation, you have to do this measurement, you have to force this collapse and get these measurement results. And that means that even if you kind of do something in the superposition to all of the different parts of the superposition, you can't then read the outcome of what that did to each part of the superposition, because when you measure it, you're just going to get one of the branches of the superposition you'll be kind of collapsed into just one of them, and that's the outcome that you'll see. So you can't kind of just access what the outcomes are that have happened to everything in parallel. So you might at first think, oh no, this means quantum computers can't really do anything useful, because how are you going to get an advantage over classical computing if you're just going to get one fixed outcome at the end anyway? Then what was the point of all this superposition? But the point is that you have to be strategic and figure out a way to kind of harness that extra space that you have in between the beginning and end of the computation, of using all this extra space you have with the superposition, and make it so that when you measure it at the end, it collapses into a state that actually tells you something useful, and that it tells you that information. You can find ways of doing that, so that when you measure it at the end, it's telling you something useful that's made use of the fact that it was in superposition before to kind of orchestrate getting the right answer. And you can kind of see that as like, you could think of it in terms of waves, of like constructive interference and destructive interference. So that's a concept a lot of us are familiar with already from like thinking about classical waves and how they constructively interfere to make high amplitude regions, or destructively interfere to kind of cancel out and essentially either add up or cancel out a signal of some kind. And so you can kind of make that happen with these quantum waves, these quantum states, and what you want to do is use the superposition to make your correct answer add up and your wrong answer cancel out. And then when you measure at the end, you measure a fixed state, but it's kind of got a high chance of being this correct answer. So to kind of come on to your second question of like kind of what they can be applied to is different to classical computers, what you find is that for certain problems with a certain structure, you can create algorithms that work on quantum computers that kind of do this thing of amplifying the correct answers and cancelling out the wrong ones. And for certain problems, we have quantum algorithms that can do those things efficiently, that can get an outcome in a kind of reasonable amount of time, whereas our best classical algorithms can't do that, can't solve that problem in a reasonable amount of time. So they're working in completely different ways. The quantum computers are kind of, you need to manipulate the algorithm to do this strategy of using the superpositions to add up or cancel out to give you a useful answer at the end. Classical computing, you're manipulating bits, and you kind of think about those algorithms in a completely different way, but you kind of have this new tool that is better for certain problems with quantum computers.
So what really makes quantum computers different are really the basic properties of quantum particles or quantum mechanics, like superposition and entanglement.
Yeah, exactly. Yeah. So the superposition and entanglement are kind of these ways that you create the ability to explore this whole quantum space of states that you just can't access with manipulating classical bits.
Mm-hmm. You mentioned information and how it's manipulated in quantum computers in a different way as compared to the classical ones. So when I think of classical computers, we know there are processors with transistors, and basically zeros and ones are presence and absence of charges on some part of the circuit.
Mm-hmm.
When I think of quantum computers, what should I really think of physically?
Mm-hmm. Yeah, it's an interesting question, because physically, at the moment, there's lots of different ways that we can create quantum computers, and there's no standard way yet. So there was a stage in the past where people were thinking about different ways of making classical computers, and they kind of started out with these vacuum tubes and these other ways of creating classical computers, but then we all kind of converged on transistors being the best way to build a classical computer, and now classical computers are all kind of built on the same hardware. But there's no reason that they have to be on that hardware from a kind of fundamental physics perspective. Anything that you can encode bits on, you can use as a classical computer. And with quantum computers, it's similar, that anything that you can encode quantum bits on, you can in principle use it as a quantum computer. And since everything around us is described by quantum mechanics to the best of our knowledge, then anything that you could think of that acts as a quantum system could be used as a qubit. But you have to be able to control it, and that's where the kind of difficulty comes in, and that's what ends up selecting a few particular ways where we have an idea for how to do that. So I find the most intuitive one I find to think of is as like a physical manifestation of a qubit from which you can build quantum computers, is to think of a photon, a single particle of light. So you could create a qubit from a photon, and one way of doing it is to use a beam splitter. So that's a kind of half-silvered mirror, and if you send a photon through a beam splitter, then it will then enter a superposition of going straight through, being transmitted, or being reflected from the beam splitter. So it kind of goes from having one pathway to a superposition of two pathways, straight ahead and reflected. And that is a kind of basic example of a quantum gate, a quantum operation, because you have gone from being in one state, so say the straight ahead pathway, to a superposition of states, the straight ahead pathway and the upwards pathway, for example. So that's one way you could make a qubit. You could also make it from another one that's quite nice to imagine, is like the energy levels of atoms or ions. So you can imagine kind of exciting an electron in an energy level of an atom, and then exciting it to a different energy level that's like higher energy, and then controlling superpositions of the electron being in those two energy states, and using that as your qubit, as your two levels that are put in superposition. And you could control that. For example, lasers can be used to control which states these atoms or ions are in. And another way to build them, which is the approach that's kind of very popular with tech giants at the moment, like Google, IBM, also Oxford Quantum Circuits, where I work, is using this approach, which is to use superconductors. So superconductors are these materials that we cool to very low temperatures, so not absolute zero, but close to absolute zero, very, very cold, in order to make them superconducting, which is this kind of very cool phenomenon that these materials can exhibit. And that kind of allows them to conduct without resistance. And it turns out that you can control these superconductors to create a qubit. And actually understanding what is physically happening in a superconducting qubit is quite complicated, but a nice way to think about what it is doing is that it's creating an artificial atom. So essentially you're using superconducting circuits to engineer a system with the exact same physics as an atom. So then you can imagine it in the same way as your qubit that's based on the atom, where you're creating superpositions between energy levels, and the physics of the qubit is exactly the same, except that physically you're building it kind of artificially from this superconducting circuit instead of from actual atoms. So those three are quite popular approaches at the moment. There's other ones as well. There's qubits. There's people working on having quantum computers based on silicon-based qubits, for example. And there's other kind of more exotic ideas still being explored. Sometimes some of them are at the more kind of academic research stage.
Okay, so we have superconducting quantum computers, ion-trapped quantum computers, and the photonic ones that you talked about.
Neutral atoms, which I kind of described them in the ions together. But,
right. So essentially, the physics behind these physical systems is creating a two-level system, like that of an atom. So all of the problems that we currently face with quantum computers, are they fundamentally the same across all types of computers, or do different types of quantum computers face different types of problems?
So I'd say there's overlap, particularly on a kind of high level, on what the general problems and challenges are, but the kind of difficulty, I guess which ones are kind of the most difficult can vary significantly between the different platforms. You mentioned kind of the way of doing operations. So as like a side note, in the superconducting case, that's like through microwave pulses, which is like the same, using microwaves is kind of the same technology that we find in like mobile phones and radar and stuff. So you kind of see these different aspects of these technologies from other places being used in the different quantum computing modalities. Let's see, I'll try and summarize a few of the general challenges and how it differs for the different modalities. So in general, the problem that we kind of face across the board is that quantum computers are noisy, so that qubits suffer errors. And those errors come from unwanted interactions with the environment, which then causes the qubits to essentially kind of effectively collapse into some random state when we didn't want them to. It wasn't our measurement of it, it was some like unintentional interaction. So that's the kind of big problem, difficulty with building useful quantum computers in general, is how do we build qubits that are good enough quality and have low enough errors to tell us something useful, but then you also need to scale that qubit number up. So you need to have low errors, you need to have a large number of qubits, because if you've just got say 50 perfect qubits, you can probably still simulate all of that, what you do on those classically. And you need the computation to be fast, so to tell you your result in a reasonable timescale. Because if you've got great qubits, but it'll take you 10 years to find out the answer to your problem, then it's not that useful, unless it's a really great question that you're willing to wait 10 years to hear the answer to. So you kind of have these problems of how do we make good quality qubits? How do we scale them? How do we make it fast enough to tell us something useful? For making good quality qubits, that tends to be the kind of world records for the accuracy that you can get on like single qubits and 2 qubit operations are with ion traps. So in this department in Oxford Physics Department, there have been, records set by the Antrap groups here. I think even one very recently on, showing that you can do some quantum gates with a very, very high precision. So that's something they're very good at, for example. And then, I guess more generally, this issue of controlling the errors is partly about making good quality qubits in the first place, but it's also about doing a process of quantum error correction. And what quantum error correction is essentially using a bunch of noisy qubits to encode one less noisy qubit. So that's called a logical qubit. And the kind of noisy ones are called physical qubits. And then the idea is that you encode a less noisy logical qubit using lots of noisy physical qubits. So you kind of use this redundancy of having a lot of qubits encoding the same information to be able to correct errors on your computation. And that kind of also connects with this problem of scaling, because once you need lots of physical qubits for each of your logical qubit, then you also need to think, well, now if I want 50 logical qubits, I've got to have even more than that physical qubits. So you really have to think about how you're going to build up to scale your quantum computer. With quantum error correction, different ways of doing it will be preferable for different types of hardware as well. So, for example, if you there are some codes that work well when all of the qubits are connected to their nearest neighbor. So that's this idea of like local connectivity. And the codes are the way that you encode your logical qubit in your physical qubits. And there's a famous one of those called the surface code, which kind of has lots of nice properties. And that's kind of natural to use on superconductors, for example, because they have this kind of local connectivity naturally. There's other things like trapped ions, for example, in neutral atoms. You can create connectivity between distant qubits. So that's kind of the qubits that are more connected. And then that opens up a different range of codes that you can use. So for example, you could use some codes, they're called like high rate QLDPC codes. So that means that you can pack in more logical qubits per physical qubit in your code. Mm-hmm. And so that helps you, with this scaling problem, because then you don't need as many qubits because you can pack more into the same amount. But then you then have some superconducting people being like, hey, well, we'll just engineer our hardware to have that property as well. So that's what IBM are doing, for example. Their team discovered these really nice codes that are an example of this high-rate QLDPC code. And what they're doing is actually doing some kind of engineering of their hardware to engineer connections between distant qubits, and then be able to use that type of quantum error correcting code that packs lots of logical qubits per physical qubit. So the connectivity is an aspect which is very hardware dependent, and then that needs to be kind of designed together with what the approach to quantum error correction is going to be to do that efficiently. And then the other big difference is in speed. So superconductors are kind of known for being very fast, and that's kind of why people like to use superconductors from the early days, was this kind of idea that you can get your the outcome of your computation in like a reasonable timescale, because they're very fast compared to the speed of say, ions or neutral atoms. And then there's a completely different approach being taken by, say, Microsoft, kind of focusing on this topological qubit approach. And there's a lot of discussion in the community about like how you actually verify that you have a topological qubit, and then people are like discussing the results that they've put out, because the idea is that this qubit is kind of using an entirely new phase of matter, and that they've kind of created this new phase of matter that's like intrinsically protected against errors. So it would still need some error correction, but a lot less than kind of using normal qubits. And so, that's another, that then leads to, like if that all works, then it also has this speed advantage. Still have to find a way to do the error correction in a good way. So that's, this kind of universal challenge for all of the platforms. I think that gives an idea. I guess the engineering challenges of scaling look very different for the different platforms. Like, the way you physically scale photonics, trapped ions, superconductors, very different. Like, obviously, superconductors, you're kind of thinking about the cryogenics, and there's other platforms that also have cryogenics, but they're going to like different temperatures, and you build it in a different way, so you're kind of thinking about scaling that in a different way. And there's also the question of like the size of the physical quantum systems. So I know that, with trapped ions, for example, there's different approaches, and they can have like a vastly different physical footprint. So there's the question of like, what your physical footprint is, and then that feeds into the engineering of all your control hardware and cryogenics to fit in a space and not interfere with each other and so on. So that can look very, very different.
Mm-hmm. Right now, are all the people who are using quantum computers, are they just all researchers, or is it being used for real life applications?
There's people who are interested in using them for commercial applications that are doing kind of proof of principle studies. So the idea is that they're in different industries that want to take advantage of quantum computing when it is at a stage where it can provide advantage. So they might be, there's people interested in the energy industry, for example, or in finance, and in a lot of other industries. So what tends to happen, given the status of the technology at the moment, it's this came up in the questions you asked at the beginning. Quantum computers have been used to perform some tasks faster than a classical computer can do, but those tasks haven't been useful tasks. They've been actually kind of tailored to be something that a quantum computer is particularly good at. So we've yet to reach the point that people think of as like quantum advantage or like commercial quantum advantage, where a quantum computer does something useful faster than a classical computer can do. And people expect that that'll start with kind of scientific advantages. So I guess at that stage it'll still be researchers in a sense using them, but for advantage. But instead of using them to do quantum research, they're using them to do some other research that is like making use of the quantum hardware to help them with that. And then probably the stage after that is when it'll be kind of commercially useful. So right now, what people that want to use them in the future to get an advantage are doing is proof of principle experiments where they'll think of a problem that they have and a quantum algorithm that has some expectation of being faster than a classical computer on a large scale, and then figure out how to implement it on a small scale so that there's a kind of prototype for when there is a quantum computer available that is at a large enough scale to get advantage with that problem, it can then be run on that. So that's kind of what people are doing at the moment. And yeah, we need better quantum computers to really put them through their paces for actual applications.
Mm-hmm. Is there any rough idea about when do we get the actual better quantum computers?
Yeah, we have different... So, yeah, the biggest efforts to build quantum computers on a large scale are from companies. So that's, that's where we look at for where we're going to have a large scale quantum computer, is to look at what is the industry doing. And various companies have put out roadmaps of what they expect to build and for when. So the company I work for, AQC, has put a roadmap out recently, kind of outlining different different scales of quantum computer that we expect to build in different timelines, and then what the potential applications of those quantum computers are, like given our current knowledge of quantum algorithms and applications research. So a term that's come to be used recently to kind of discuss eras of quantum computing is QOPs. So this is reliable quantum operations. And we have this idea of the mega QOP is the scale at which we have like 1 million error-free operations. The giga QOP is where you have 1 billion error-free quantum operations, and then tera QOP is where you have 1 trillion error-free quantum operations. So we can kind of think in terms of those regimes of like, when are we going to reach each of those scales? And the kind of current expectation of the community is that the mega QOP scale is where we're going to see the kind of first advantages of quantum computing for some particular problems. But it's not going to be kind of widespread advantage at that point. It'll be the kind of specialist things that can really optimize everything to make use of the number of accurate qubits that we have at that scale. Then gigaQOP, there'll be kind of more applications, and that's when it'll kind of become more widespread, that there'll be like applications that you can kind of reliably get an advantage from a quantum computer for. And then teraQOP kind of really unlocks like a really wide range of applications, including things like breaking encryption, at least the way that we encrypt data today, which is RSA encryption. So so you can kind of ask, when do we expect to have these eras? And what kind of something the community is aiming to do at the moment, and the UK has this on their kind of quantum plan, is to have a mega QOP quantum computer by 2028. And some places are aiming for it for like 2029, but you kind of have this idea that around, I think I've seen in quite a few places the kind of notion that by the end of the decade we have mega QOP scale. That's kind of what people are saying. So so that gives kind of some indication of what kind of people are expecting for the different regimes, and it's very difficult to predict the future because all these things kind of really depend on unpredictable human innovation and research. Like, there's been really interesting developments over the last few years on all different aspects of the quantum computing stack that you can't really have predicted beforehand. So yeah, so definitely kind of reaching those larger scales is kind of difficult to predict because of the difficulty of kind of how do you predict what ideas people will come up with on like reducing the resources of different parts of the stack and so on. But at least for this kind of first milestone, that's kind of what people have in mind of the first kind of scientific and commercially useful applications that have an advantage over classical computers kind of popping up in that interesting megaquark regime in a few years' time.
Mm-hmm. What is it that excites you the most about this quantum computing space? And how did you get into this in the first place?
The thing that excites me the most is really thinking about pushing our technology right to its limits, and this kind of underlying idea that we're really using, like when we, I guess when we did actually need to know about quantum mechanics to develop today's classical computers, because understanding semiconductors that all our electronics are based on needs quantum mechanics to understand it. But you need this kind of quantum information theory to then do quantum computing is kind of a next level up. So people kind of call the electronic side like kind of quantum 1.0 technologies, and then this quantum information stuff is like quantum 2.0. And I like this general idea that like by discovering new laws of physics, those of quantum mechanics, we've discovered like a completely new way of processing information and like doing this, it's a kind of funny connection there that kind of new physics leads to new computation. Like there's something quite deep in that, and it's, I like this broad idea of how can we push our tech to its limits. Like it'll enable us to do things that you just can't do with your classical computer. Like it just opens up this new space. And I like to, think about kind of in the limit of when we have really great, really useful, really kind of large, low error quantum computers. What are all the ways that we could really be creative with that and use it for fundamental science? Like that's my background in my PhD is in like foundations of quantum information science, and really thinking about kind of fundamental physics and what it tells us about reality. And that's always kind of what really excites me the most, is thinking about like how can we use use those fundamental insights to create cool technology, and then use the cool tech to then test cool things about the fundamental insights. So one of the things that's kind of cool about the idea of quantum computing, and which is where the idea of quantum computing actually came from, was thinking about how to test the many worlds theory of quantum mechanics against the Copenhagen interpretation. So that's kind of thinking about, if you think about a Schrödinger's cat thought experiment, and then you've got the cat in superposition of being dead and alive, and then an observer looks at it and it collapses to dead or alive. The many worlds interpretation will say that the cat really is in a superposition of being dead and alive, and when the observer looks at it, the observer enters that superposition, becomes entangled with the cat, and then one version of them sees the cat dead, one version sees the cat alive, and it appears to have collapsed from the perspective of each observer, but in reality both observers kind of exist, and both versions of reality are real. So that's why it's called the many worlds interpretation. Whereas the Copenhagen interpretation would say that observers collapse a quantum state, so either the cat kind of collapsed whatever was going to kill it in the box into one state because the cat's an observer, or if the cat doesn't count as an observer, then whoever looked inside the box caused it to collapse. But either way, whatever an observer is, the idea is that an observer looking at a quantum system causes an irreversible collapse instead of both realities happening. And the physicist David Deutsch was trying to think of a way to test between these two interpretations, because a lot of people were saying that it's kind of just philosophy, like that they're actually all these two ways of thinking about quantum physics are equivalent. But he imagined simulating an observer measuring a quantum system on essentially on a quantum computer, though he didn't call it that at first, and then imagining trying to reverse that measurement. And you can actually consider doing an experiment where you get a different outcome depending on whether you got this irreversible collapse or whether it was just an entanglement, as the many worlds interpretation says. So if we ever figure out how to simulate observers on computers, and there might be a very long way to go to know how to do that, but if we could figure that out and we have really good quantum computers, then we could actually start doing these like crazy simulations where we simulate observers, or I'm sure there's like even more cool and exotic experiments that you could do with testing quantum mechanics on those scales if you're really processing lots of quantum information. So that's kind of what I think is really cool, like in the long-term future of like the limit of pushing our tech to the limit. And then what got me into quantum computing, it was kind of after, so I'd say my interest in these kind of fundamental aspects of quantum physics came first. So that came in kind of high school, like reading popular science, reading about these paradoxes in quantum mechanics and the counterintuitive aspects of it is what got me interested in physics, and then I wanted to look further into that. And then I realised kind of near the end of my undergrad physics degree that quantum information is kind of the particular subset or branch off in the space of quantum physics that's actually dealing with the stuff that I thought was really cool. Kind of found quantum information science was kind of my thing, and had really nice tools for understanding superposition and entanglement. I found it quite satisfying, kind of expressing things in terms of qubits and manipulating qubits and so on. And then I came across quantum computing and then found out that you can actually access quantum computers on the cloud. And so IBM had put up their devices already on the cloud that you can actually access from your laptop and like run something on them. So I started like running something, putting my own qubits in superposition on the cloud, and I thought that was really cool because I was like, oh, I've actually put a qubit in superposition and like measured it, and I actually did that myself, like I actually put something in superposition. So I was quite excited about that, and then I wanted to get into learning how to code quantum computers because I'd seen that it was a thing that you could use this programming language Qiskit to code these quantum computers. And so then I thought it would be cool to like get a group together to work on doing that together. Then thought I might as well start a society. So I started Oxford Quantum Information Society, and then use that to kind of, one thing was getting a group of people together to code quantum computers, but then also kind of organising events to do with quantum computing, but also these kind of fundamental aspects of quantum information. So really keeping those two sides. But I'd say kind of from that point on, there was always a quantum computing strand that I kept going along, kind of alongside the foundational science, or kind of sometimes intersecting.
Mm-hmm. Cool. It was so lovely to talk to you. And do you quickly just want to plug in your podcast?
Yeah, sure. I have this Quantum Foundations podcast that I started just over a year ago. So that's on my YouTube channel, which is just my name, Dr. Maria Violaris, on the YouTube channel. It's also on audio platforms. I have a combination of episodes that are aimed to be accessible to whoever's interested, and then some episodes are kind of mathematical for people who already have a background in quantum mechanics and quantum information theory. So those ones are on the YouTube channel. The audio ones are the kind of accessible ones only. And they cover topics like locality and why there's no spooky action at a distance, despite many people thinking that there is. The many worlds interpretation, like I mentioned in this, and lots of other cool aspects of quantum foundations. And yeah, I also post other videos about quantum science and tech on my YouTube channel, like reaction videos to quantum chips and other, just fun quantum content.
Cool. Thank you so much. It was lovely talking to you.
Yeah, it was fun to chat. Thanks for having me on.